All right, camera's still working. Very good. So yeah, basically when I wrote the proof down, I omitted a couple words which have made it hard for me to understand my proof because I'm a dummy. So basically, suppose, suppose K has maximum K1 for u equal to E1, right? So K of E1 equal to K1 E1 by assumption, all right? And as I explained, that's a reasonable assumption because we know K, the principal curvature function, is continuous, and we're feeding a continuous function, things from a unit circle, which is compact, so we know it has to take a maximum. So suppose K1 is the maximum. And then the next step is to pick E2, you just pick E2, which is, perpendicular to E1. So, well, there are really two choices, right? Either plus or minus 90 degrees once you pick a, right-hand rule, so to speak. But anyway, so choose E2, which is perpendicular to E1. That's not an unreasonable step, all right? So that makes E1, E2 an orthonormal basis. And what's left to show is that K2E2 is equal to K2E2. That is not yet known. We need to prove that. And we also would like to see that, that K2 is the minimum of K, right? So the umbilic case is like not particularly interesting. Then K is constant in all directions. If K is constant in all directions, then it's a scalar multiple of the identity map, right? There's not really much to prove in the umbilic case. So the non-umbilic case is where we're focusing all our attention. All right, so we've picked this E2, and so whenever you have an orthonormal basis, you can expand a vector in terms of like dot products with respect to the orthonormal basis, right? Usual component expansion stuff. U dot E1 E1 plus U dot E2 E2. All right, and because U is a unit vector, you can pick an angle such that this is cosine theta and that's sine theta, because you know that this squared plus that squared has to be 1, which means you can identify it with a cosine and a sine, right? And so he defines g of theta to be k of u, because u is identified with theta in that way, right? So g of theta is going to be k of u, which of course is s of u dot u, which in this case is s of cosine e1 sine e2 cosine dotted with cosine e1 sine theta e2, right? Now we introduce a, b, c, d, the basis, the matrix of the shape operator with respect to the basis e1, e2, all right? So I suppose if you want to be more pedantic and kind of link with my larger discussion of linear algebra, I would say, okay, so let beta equal to E1, E2. There's my basis for tangent space at P of M, and this is really the basis, the matrix with respect to the beta basis to the beta basis, right? But I kind of follow O'Neill and don't clutter things with this explicit denotation to indicate the basis with which we're calculating the matrix of the linear transformation, all right? And that's not unusual in higher mathematics to like kind of omit some of the coordinate map stuff that I made explicit in our discussion of linear. But in any event, so we have A and B and C and D, except we don't have C and D because we know that it is symmetric by the previous discussion in the last video, right? So since it's symmetric with respect to all bases, it's certainly symmetric with respect to this one, which means that we don't need a B and a C. We can just put B here and there. So that's good, right? And so when you do all that, you get g of theta is cosine squared theta A, B, and C here with the two sine cosine and sine squared over there. So there's the formula for g of theta. It's a cosine squared theta plus c sine squared theta plus 2 cosine sine b, where a, b, and c are the to be determined entries of the matrix of the shape operator with respect to this orthonormal basis, half of which was given to us by the extreme value theorem. Now, so, all right, since K1 equal to K of E1 is the maximum normal curvature, and also that happens what? That happens when theta equals to 0. So theta equals to 0 has to give us a maximum, right? G of 0 is the maximum. That's by assumption. Now if we differentiate with respect to theta, we get, and this is just plain old calculus 1 here, folks. So G prime, minus 2 sine, this differentiates to minus 2 sine cosine, this differentiates to 2 sine cosine, and that differentiates to cosine squared minus sine squared, like so, right? That's G prime of theta. Now we know that G prime of 0 is 0 because, remember, G of 0 is a maximum, so by Fermat's theorem, G prime of 0 must be 0 as it exists, but G prime of 0 is also equal to 2b by just plugging in, only this term remains, 2 times 1 times b, 2b. 2b or not to b? Apparently not. So b is equal to 0. Actually, 0 is still something, right? So anyway, G prime prime, or double prime if you like. Anyway, I'll stop being an idiot. That's not true. It's part of my brand. G prime prime of theta is, well, I'm differentiating this again. I just found out b was 0, so I can ignore that. And that's also the same term twice, right? So that's twice c minus a times the derivative of sine cosine. Right. So G prime prime is this. Of course, the derivative of that is cosine squared minus sine squared. All right. And but G prime prime of 0 is a max, which means the second derivative must be negative, or at worst 0. So if this is less than or equal to 0, that means that, but the thing is, we also know that theta is 0. This can't be negative, so it has to be this that's non-positive, which tells us that A is greater than or equal to C. Oh, by the way, B being 0 was nice because that proved that the matrix was diagonal, and now we also know that A is greater than or equal to C. But what is A and what is C? Well, when you think about the matrix here, we have S of E1 is AE1, and S of E2 is CE2, and so in other words, E1 and E2 are eigenvectors with eigenvalues A and C, but we already know that A is equal to K1 by assumption at the start of the proof, and C is K2. That's the other eigenvalue. What's the relation of K1 and K2? A is greater than or equal to C, which means that the other eigenvalue is either equal to it or it's smaller than it, as predicted. And however, in everything I've said so far, I guess it's not. I mean, how do you know that that's the minimum that? The question is, how do you know that there aren't, that, I mean, yes, that's the maximum. Yes, this is also an eigenvector. Great. How do I know that that's the smallest, the minimum value that K takes is K2? I suppose, well, I don't know, maybe it's obvious from the things we've done, but I don't see it right off. I mean, again, this is, if you already have proved the real spectral theorem in another course, this is somewhat redundant. Once we know that the shape operator is, symmetric, then we can apply the real spectral theorem, and the real spectral theorem says that, what's the real spectral theorem say? It says, since, the shape operator at the point P is a mapping from TPM to TPM, is symmetric, that implies that there exists, orthonormal eigenbasis, which I will call E1 and E2, right? And with, SP of E1, I used lambda in my previous talks about this stuff, lambda 1 E1, and the shape operator acting on E2 is lambda 2 E2, right? And if you build an arbitrary vector with constants, let's say like, well, all right, so if I build, I think I'll use x bar and y bar, x bar E1 plus y bar E2, then this works out to well, lambda 1 x bar E1 plus lambda 2 y bar E2, I believe. And then if we calculate the curvature in the u direction, well then that's going to be the shape operator acting on u dot u, right? But here x bar is equal to, if I call this whole thing, let's say u, x bar would be like u dot E1 and y bar would be u dot E2 because E1 and E2 is orthonormal. So this becomes lambda 1 u dot E1 plus lambda 2 u dot E2, that's S of P, SP of u, that's the shape operator acting on u, and that gets dotted with u, which for arbitrary u, I guess, would be again u u dot E1 plus u dot E2. Okay, great. But the thing is, E1 dot E2 and E2 dot E1, those are 0, so we only have to worry about like this with that. And so we get lambda 1 u dot E1 squared, right, with E1, plus lambda 2 u dot E2 squared, right? And notice that the length of u is assumed to be 1. So if we say that, the angle between u and E1 is theta, then this becomes lambda 1, cosine theta squared, right? And then what is E2? E2 is either this one, come on, it's either this one, right? Or it's that one. Because it's perpendicular to E1, right? So what's u dot E2? Well, it's either got like angle theta plus 90, or it's got angle basically if the angle between u and E2 is theta, it's either theta plus or minus 90, right? Is that right? Or is it, that's not quite right. It could be theta plus 90, or if it's down there, or it's 90 degrees minus theta, right? So how does cosine, what happens with cosine of theta plus 90? Well, you get cosine theta, cosine theta sine 90 minus sine theta sine 90, right? Or you get cosine of 90 minus theta. And so adding angles formula, I'm thinking through cosine 90, cosine minus theta, or minus sine of minus theta, sine 90, right? So basically, cosine of theta plus 90 or cosine of 90 minus theta, it's either plus or minus sine theta. When you square it, you just get lambda 2 sine theta squared, right? So that takes us back to that, you know, cosine squared lambda 1 plus sine squared theta. That takes us back to Euler's formula. And of course we identify that lambda 1 is k1 and lambda 2 is k2. Of course that is up to the choice of which one's min, which one's max, whatever. My point is that this formula can be derived if we know the real spectral theorem already in this way. And I think just really if you just think about the formula, you can see that lambda 1 and lambda 2 have to be like mins and maxes here as you think about what happens with the cosine and the sine, right? Like when cosine when cosine is 0, sine is plus or minus 1, right? So that means you can get the plus or minus lambda 2. Except you can't get the plus or minus. You can just get the lambda 2 because it's sine squared, right? When sine is 0, cosine is plus or minus 1, but it's squared, so it just get lambda 1. So basically lambda 1 and lambda 2 are like extreme values for this expression. Because the sine and the cosine can't ever get larger than 1 or minus 1. So when you square them, they're stuck between, the absolute value of cosine and sine is stuck between 0 and 1. It's not quite a proof, but it gives you a sense of it. Anyway, so there it is. Euler's formula for normal curvature. He also describes, at the end of that section, kind of a special way of thinking about how the normal curvatures relate to the shape of the surface at the point. So the setup for this discussion is you're looking at the point being the origin. You're basically setting up coordinates that make the point you're thinking about be the origin, and make the tangent plane the xy plane. And in so doing, you're assuming then that if you want to think of the surface as being the graph of something with respect to this coordinate system you're inventing, it would have x and y partial derivatives to be 0, and it would just be captured by its quadratic expansion. Like so. But there is a reason that the middle term has to go away, and I think this actually relies on an exercise in the text, which I don't know if I have assigned you guys or not, but if you work that exercise, then you can understand why this middle term goes away. And in short, the graph, with this setup, the graph of the surface, you can look at it as just being z is equal to the weighted sum of x squared and y squared, where the weights are given by the principal curvatures. And I think this is useful because it gives you a little bit, a little bit more kind of insight into what the different principal curvatures mean. If one is 0 and the other one's negative, you have like a trough where the surface is bending up towards the well, you could either have K2 be positive or negative. Actually, it's not. It's kind of ambiguous here. And trying to remember. Okay, yeah. So K2 negative. I think the normal. I think we're assuming that the normal points upward in all of these. Yeah, normal upward. So. But anyway, so K1 0, K2 less than 0. If you had K2 greater than 0, I say less than 0. I don't know if I believe that. I don't believe that. I think this picture that I've drawn is for K greater than 0. I think the picture I've drawn is for K greater than 0, because if you look at it, z equals to positive number times y squared. Well, that would be a trough that opens up with the usual xy coordinates. So I think that's a typo in my current notes. I don't know if I copied the picture down wrong from the book. Or what is more likely is I just copied the inequality wrong. What's also possible is that this picture is not in the book and I just made it up. But I don't remember at the top of my head. So there we go. Better. All right. This one, K1 and K2 both positive, so it's like Z is equal to, you know, it's a paraboloid basically, right? It's an elliptical paraboloid, generally speaking, and it's lifting up. If they're both negative, then it's an elliptical paraboloid that's opening down, right? And so when the principal curvature is negative, that means the surface is bending away from the normal. When the principal curvature is positive, it means the surface is bending towards the normal, right? And when one of them's positive and one of them's negative, that means in some directions the surface is bending up towards the normal, and in another direction it's bending away from the normal, as is the case with this saddle shape here. All right. So that brings us to the study of Gaussian curvature. And I think what I'm going to do is I'm going to start again here, and I'm going to marry this material together with the calculational techniques, because really these formulas here, they all feed into the discussion in section 5.4, which I think should go together with this. So I'm going to stop it right here for now. Thanks, guys.